Is there anybody who doesn't have the 3.4 lecture notes that I gave an introduction to yesterday? Everybody have? So yesterday, I gave you a brief introduction at the end of class yesterday on what a rational number is. Okay? And so, under certain circumstances, when a polynomial function has integer coefficients, if one of the zeros is a rational number, we can come up with a set of rational numbers that zero must come from, right? So that we don't have to consider all rational numbers, but just rational numbers in this set of rational numbers. Okay? And so instead of reading through the formal definitions, you can read that on your own. I think I'll demonstrate the definition with the first example. So you're given the polynomial function p of x is equal to x to the fourth minus 3x cubed plus x squared plus 3x minus 2. Now riddle me this. What's the constant term in this polynomial function? From our definition of polynomial function. What's the constant term? It's not here all by itself. Minus 2, right? It's not being multiplied by x. So minus 2 is the constant term. And what's the leading coefficient? 1, right? It's coefficient in leading term. Leading term is the term with the largest power of x. Largest power of x is 4. And so it's the invisible 1. Okay? So 1 is the leading term. Okay? So with just those two numbers, we can come up with a set of rational numbers so that if there is a zero of this polynomial function that is a rational number, it has to come from that set of numbers. Okay? So we don't have to consider an infinite number of rational numbers, we just consider a finite set of rational numbers. Okay? So what we have to consider in developing this set is the factors of the constant term and the integer factors of the constant term and the integer factors of the leading term. Okay. So the integer factors of minus 2, constant term, are minus 2 and 1, or two factors, right? Because minus 2 times 1 is minus 2. And plus 2 and minus 1. Because 2 times minus 1 is negative 2. Those are the only integer factors of minus 2, right? And so, in short, we can write those 4 integer factors of minus 2 is plus and minus 2 or plus and minus 1. Now we consider the integer factors of the leading term. And that's pretty simple. The integer factors of plus 1 are just 1 and minus 1, right? 1 times 1 is 1, minus 1 times minus 1 is 1. Which we can write as plus and minus 1. Now we can come up with a set of possible rational zeros, rational numbers, a set of possible rational numbers that will make, when plugged in for x on the right-hand side, the right-hand side will equal 0. Okay. Now it doesn't guarantee that any of those rational numbers will make the right-hand side equal 0. But if there is a rational number that will make the right-hand side equal 0, it's going to come from this set. Okay. So we're going to come up with a list of possible rational zeros. Okay. And to find that possible list, you take the integer factors of the constant term and divide them by the integer factors of the leading term. Here's the integer in the numerator. Was the integer factor of the constant term minus 2. And you divide it by the integer factors of the leading term 1. Okay? And that's what, in your definition, that's what this is saying right here. The set of possible rational zeros, you take the factors of the constant term, and you divide it by the factors of the leading coefficient. And that gives you the set of numbers, okay? Set of rational numbers. So, in this case, so we take each number, each factor of the constant term minus 2, and we divide it by each factor of the leading coefficient. So we got to take minus 2 and divide it by 1. And take minus 2 divided by negative 1. Take plus 1 divided by 1. Take plus 1 divided by negative 1. Okay. So first I'm going to take all these 4 numbers and divide them by 1. So what do I get? Minus 2 over 1, 1 over 1, 2 over 1, and minus 1 over 1. Now when I take these same 4 numbers and divide them by negative 1, I actually end up with the same 4 numbers all over again. So you really only have to divide the integer factors of the constant term by the positive factor of the leading term. When you divide them by the negative factors of the leading coefficient, you just end up writing out the set a second time. And so these numbers are minus 2, 1, plus 2, negative 1, which can be written in short as plus or minus 2, plus or minus 1. So if there's a rational number that makes the right-hand side equal to 0, it's going to be one of these 4 numbers. So you don't have to consider every rational number, just these 4. Okay. So lastly down here it says, to use the rational zero test, you list all the possible rational zeros, which we did, those 4 numbers, and then you got to use trial and error. There's no magic formula. You just plug in and check to see if it makes the right-hand side equal to 0. So plugging in 1 minus 1 is the easiest, right? The easiest math. So I check the value of the polynomial function at x equals 1. So I have p of 1 is equal to, and when I put in 1 in for x, right, 1 to the 4th is 1, 1 cubed is 1, 1 squared is 1, okay, right? 1 is 1. And so when you put in 1 for x, you just end up adding the coefficients. 1 minus 3 plus 1 plus 3 minus 2, which is equal to 0. So x equals 1 is a 0. Right? Putting 1 for x makes the right-hand side equal to 0. So by the factor theorem, that means x minus 1 is a factor. Okay. So our 4th degree polynomial over here can be written as x minus 1 times some 3rd degree polynomial. Okay. Well, I also checked minus 1, see if it was 0. And when I put in minus 1 in for x, right, you got minus 1 to the 4th minus 3 times minus 1 cubed plus minus 1 squared plus 3 times minus 1 minus 2, and that's equal to 0. So x equals minus 1 is a 0, which means x plus 1 is a factor. So we can write the right-hand side now is x minus 1 times x plus 1 times some unknown quadratic. Okay? We got to find that quadratic so we can find the last two zeros of this polynomial function. Okay? Well, before we can find the quadratic, we got to find this 3rd degree polynomial. So how do we do that? We divide this 4th degree polynomial by x minus 1. That'll give us the 3rd degree polynomial. And then we're going to divide the 3rd degree polynomial by x plus 1, and that'll give us the quadratic. Do we have to do long division? No, because it's linear, right? X minus 1 and x plus 1 are in it, so we can do synthetic division. So let's divide. Can I erase this? Does everybody understand the steps here? Yeah. So let's divide our 4th degree polynomial by x minus 1. So 1 goes in the box, and then we write out the coefficients of p of x and descending powers of x. So we got 1 minus 3, 1, 3, minus 2. And now you know the procedure, right? Bring down the 1. Multiply by 1, you get 1. Add it to negative 3, you get negative 2. 1 times negative 2 is negative 2. Add it to 1, you get negative 1. Negative 1 times 1 is negative 1. Add it to 3, you get 2. And 1 times 2 is 2. And you minus 2 plus 2 is 0, and your box is the last number. Yes, ma'am. Say what? Well, technically, because once I do the division here, okay, this is gonna be a quadratic, and we know how to set a quadratic equal to 0 and solve for x, okay? Yeah, but you're correct, right? That the other numbers could also be factors, could also be zeros, right? And you could test those, right? All right. So the remainder r is 0, which shouldn't surprise us if x minus 1 is a factor. Okay. And so these coefficients go with the third degree polynomial. Right? You go from right to left. So 2 goes with is the constant term, minus 1 goes with x, minus 2 goes with x squared, 1 goes with x cubed. And so our quotient from this division is x cubed minus 2x squared minus x plus 2. So what goes in parentheses here is x cubed minus 2x squared minus x plus 2. Now you notice that the constant term here is plus 2, and so the factors of plus 2 are the same as the factors of minus 2. And the leading coefficient here is 1, just like it is up here. So if x plus 1 is a factor of x of the fourth degree polynomial, it's got to be a factor of the third degree polynomial, right? The third degree polynomial has to contain this factor. This third degree polynomial has to be equal to x plus 1 times this unknown quadratic. Yes, ma'am?
Excuse me, sir, you could also do x minus 1, and then you could also do synthetic division with x minus 2 or x plus 2, and you would still get the same answer?
Well, we don't know if minus 2 or plus 2 are zeros of this.
But if we did know that they were zeros, it would work.
If we knew they were zeros, then it would work.
Okay.
Okay. All right. Yeah, then it would work. Yeah. So we could have done synthetic division where we did x plus 1 first and then x minus 1. Right? The order doesn't matter. So this third degree polynomial has to be equal to the factor x plus 1 times our unknown quadratic. And so to find the unknown quadratic, we divide the third degree polynomial by x plus 1. And we do that with synthetic division. So x plus 1, right? The value c is negative 1. Right? Minus 1 is the 0. And now we write out the coefficients of the third degree polynomial, which are 1, minus 2, minus 1, plus 2. So you know the procedure. You bring the 1 down. 1 times minus 1 is minus 1. Minus 2 plus minus 1 is minus 3. Minus 1 times minus 3 is plus 3. Minus 1 plus 3 is 2. Minus 1 times 2 is negative 2. And 2 minus 2 is 0. And you box the last number. So 0 is the remainder, which is a good sign, because we're claiming x plus 1, right, is a factor. And now these coefficients go with our quadratic, right? The first number is squared, the second one with x, and the third one with x to the 0. Okay. So our quadratic is x squared minus 3x plus 2. Now it turns out, right, so to find the last two zeros, we set the quadratic equal to 0 and solve for x, right? And it turns out that this factors with whole numbers. All quadratics factor, but they don't all factor with whole numbers, right? Because you know some have complex numbers. And this factors into x minus 2 times x minus 1. So P of x factors into x minus 1 squared times x plus 1 times x minus 2. Right? We already know 1 and minus 2 are zeros. What's the third zero? Plus 2, right? So the zeros are all rational numbers for this problem. They are 1, minus 1, and plus 2. Right? When you set this last factor, x minus 2 equal to 0, and solve for x, you get x is equal to 2. Was 2 in our possible rational zeros? Yeah. Is 2 a rational number? Yes. Okay. Any questions on that? All right. So Rachel, kind of getting, I think you were like working ahead, and you saw that 2 was a 0, but that's not always going to be the case. Okay. Sometimes you get a quadratic, and when you solve it, it's going to be complex numbers or irrational numbers. Okay. All right. So let's flip over to B. We'll flip over to the next page. In this page, you get a whole lot more room to write. Now, as we go, I'm going to take some shortcuts in writing things, right? So we just take up less space. So in the next problem, we got P of x is equal to 4x cubed minus x squared plus x plus 3. So what's the constant term in this polynomial? Plus 3. What's the leading coefficient? All right. So the integer factors of the constant term 3, well, 3 is a prime number, right? So integer factors are 3 and minus 1, and minus 3 and plus 1, which we can write as plus and minus 3, plus and minus 1, right? The integer factors leading coefficient 4 are more involved, right? So, one factor of 4 is 4 and minus 4. We got plus and minus 4. But you know, 4 is also divisible by 2, right? 2 is a factor of 4. So we have plus and minus 2. And then we have 1, plus and minus 1. So to get the possible rational zeros for our polynomial function, we got to take plus and minus 3 and divide it by plus and minus 4, plus and minus 2, and plus and minus 1. And then take plus 1 up here and divide it by plus and minus 4, plus and minus 2, plus and minus 1. So we're going to end up with a set of 12 possible rational zeros for our third degree polynomial. Okay? So I'm going to start off with plus 3 and divide it by plus and minus 4, plus and minus 2, and plus and minus 1. We have plus and minus 3 over plus and minus 4. All right, I'm doing shorthand now instead of writing out each one individually. I'm doing shorthand. So we have plus and minus 3 divided by plus and minus 2, plus and minus 3 divided by plus and minus 1. Okay. So when we simplify, that'll give us our first 6 possible rational zeros. And now we gotta take plus or minus 1 up here and divide it by each of these 3. So we have plus and minus 1 over plus and minus 4, plus and minus 1 over plus and minus 2, lastly plus or minus 1 over plus and minus 1. And so we end up with this first quotient plus or minus 3/4. Then plus or minus 3/2. Then plus or minus 3. Then plus or minus 1/4. And plus or minus 1/2. And then plus or minus 1. So there are 12 possible rational zeros. Now, we know that complex zeros come in pairs, and we know that irrational zeros come in pairs. Since this is an odd degree polynomial, third degree polynomial, at least one of the zeros has to be a rational zero. The other 2 could be complex zeros or irrational zeros. But at least, because this is an odd degree, at least one has to be a rational zero. Either one, it's either going to be just one, or all 3 will be rational zeros. Okay? So we got 12. So if there's at least one rational zero, and it comes from that set of 12 numbers. Which of the 12 is it? Okay? It's not a lot of fun. Now, one thing you're going to notice about the rational zeros test is that plus and minus 1 always shows up in the set. Okay? Plus and minus 1 will always show up. And that's the easiest math to do. So I tested x equals 1, see if it was a 0. And when I put in 1 for x on the right hand side, I have 4 minus 1 plus 1 plus 3, which is equal to 7. So x equals 1 is not a 0. Okay. And then I did x equals minus 1. And so when I put in minus 1 in for x, I get 4 times minus 1 cubed minus 1 squared plus minus 1 plus 3, and I got minus 3. So my x equals minus 1 is not a 0. But you notice something. There's a sign change in the value of the function from x equals minus 1 to 1. Remember the intermediate value theorem that we learned about? The graph of this polynomial function must cross the x-axis, right? Between x equals minus 1 and plus 1. Okay. So just to give you a quick view, x, y, the point minus 1, minus 3 is on the graph. And the point 1, 7 is on the graph. Polynomial functions are continuous. So to go from here to here, the graph has to cross the x-axis. So there's a 0 between x equals minus 1 and plus 1. Now, unfortunately, we have a lot of choices, a lot of possible zeros, rational numbers between minus 1 and plus 1. But it helps kind of narrow things down. Yes, ma'am?
How did you get negative 3? Because you get negative 1.
Here?
Yes.
Well, this is equal to minus 4, minus 1, minus 1, plus 3. Okay. So, so remember in the intermediate value theorem, I started looking for possible rational zeros between minus 1 and plus 1. And so the next one I checked was x equals 1/4. And when I did the arithmetic, I got 13/4. So x equals 1/4 isn't a 0. And then I did minus 1/4. You see what it means on page 1? Use trial and error method. That's what I'm doing. Trial and error. I'm plugging in possible rational zeros, trying to find one that makes the right-hand side of our polynomial function equal to 0. So I did minus 1/4, and I got 21/8. For a minute, I was starting to think I was going to have to test every one of these to find the one that makes the right-hand side equal to 0. And then I did minus 3/4. And when I did minus 3/4, I got 0. As Theo pointed out, you gotta be careful with the math, don't you? Okay? You gotta be really careful with the math. Okay? So x equals minus 3/4 is a 0, which means x plus 3/4 is a factor by the factor theorem. So our polynomial over here, p of x, can be written as x plus 3/4 times some unknown quadratic, second degree polynomial. How do we find the quadratic? Divide the third degree polynomial by x plus 3/4, right? Can I erase this? So we're going to divide our third degree polynomial by x plus 3/4 to find out what this quadratic is. So c in this case is minus 3/4. It goes in the box. And then we write out the coefficients of our third degree polynomial. 4, minus 1, 1, and 3. Step procedure, bring down the 4. Now minus 3/4 times 4 is minus 3. Minus 1 minus 3 is negative 4. Minus 3/4 times negative 4 is plus 3. 1 and 3 is 4. Minus 3/4 times 4 is negative 3. And 3 minus 3 is 0. And you box the last number. So the remainder is 0. So I'm confident that I didn't make a math error when I evaluate f of minus 3/4. So our quotient, 4x squared minus 4x plus 4. So that's the unknown quadratic that goes in parentheses here. Well, can anything be factored out of this? What can be factored out of this? 4. So we have x plus 3/4 times 4 and x squared minus x plus 1. So to find the last two zeros, we set this quadratic equal to 0 and solve for x. Are the last two zeros rational numbers? Can you tell? Think so? Yeah, they're not, right? So remember I said there was either 1 or 3 rational zeros to this polynomial? There's only going to be 1. So we set the quadratic x squared minus x plus 1 equal to 0. And so we have a is equal to 1, b is equal to negative 1, c is equal to 1. And now you got to use the quadratic formula. X is equal to negative b, which is the negative of negative 1. Plus or minus b squared is minus 1 squared, minus 4 times a, which is 1, times c, which is 1, over 2 times a, which is 1. You gotta simplify. The negative of negative 1 is plus 1. And the dividend, not the dividend, the determinant under the radical is equal to the square root of minus 3. Well, division does not undo addition and subtraction, does it? So 1 has to be divided by 2, and square root of minus 3 has to be divided by 2. So we have 1/2 plus or minus square root of minus 3. It's not a real number, is it? So how do we write that? I root 3. So our last two zeros, okay, are complex numbers. Right, they didn't come from our possible list of rational zeros. So, to write out all the zeros now, x equals 1/2 plus square root of 3 over 2y is 1, 0. X equals 1/2 minus the square root of 3 over 2y is the second 0. I'm now writing them out in standard form, a plus bi form. And the last one is the rational 0, x equals minus 3/4. And to over here, the complete factorization of p of x, pull the leading term 4, right? Because how many in the homework, right, when you were doing the complete factorization, you would forget the leading coefficient, right? This 4 here is the leading coefficient. We have times x plus 3/4. And then the last two factors, you do x minus the right hand side, right? So we have x minus 1/2 minus the square root of 3 over 2y, and x minus 1/2 plus the square root of 3 over 2i. That is the complete factorization of this polynomial function. Okay? Yes, ma'am.
Is it always x minus the right side when you do those?
Yeah. Yeah, because the factor theorem says if x equals c is a 0, then x minus c is a factor.
Okay.
Okay? Any questions on that? Fun stuff, isn't it? Okay. All right, so let's flip over to example 3. You'll notice on page 1 there was no example 1, so this is really a typo, but you know how to get. You don't get upset over typos. All right, so in example 3a, we have f of x is equal to x to the 4th minus 5x cubed plus 3x squared plus x. We got to find all the values of x that make the right hand side equal to 0, right? You got to find the zeros. What's the constant term?
0.
0. Can this be factored?
Yeah.
Yeah, what can we factor? What's x, right? The lowest power of x is x to the 1st. So immediately we can factor out an x. So x times x cubed minus 5x squared plus 3x plus 1. So now we have a 3rd degree polynomial inside parentheses. We want to find all the values of x that make this 3rd degree polynomial equal to 0. right? So we're gonna apply the rational zeros, possible rational zeros test to this third degree polynomial. Okay? We're gonna find the zeros of x cubed minus 5x squared plus 3x plus 1. Well, what's the constant term of that third degree polynomial? What's the leading coefficient? This is going to be a really small set of numbers, isn't it? So the integer factors of 1 you know are plus and minus 1, right? So the integer factors of the constant term 1 are plus and minus 1, and the integer factors of 1 of the leading coefficient are plus and minus 1, right? So the possible rational zeros are minus 1 and plus 1. And we know that that third degree polynomial has to have at least one rational zero. Since there are only, I guess there could be a repeating rational zero. Right? We know that zeros can have multiplicities. So just because we only have minus 1 and 1 in our set, we still could have 3 rational zeros, right? One of those could be repeated. All right. So see if any of these are zeros over a third degree polynomial, right? You got to plug in 1 and or minus 1. So I did the easy one first. I did plus 1 first. Put 1 in for x. You have 1 cubed minus 5 times 1 squared plus 3 times 1 plus 1. And when I did that arithmetic, I got 0. So x equals 1 is a 0, which means x minus 1 is the factor of our third degree polynomial. Okay. So over here, we can write this on the right hand side as x times x minus 1 times some unknown quadratic second degree polynomial. So to find that quadratic, we're going to divide our third degree polynomial by x minus 1 using synthetic division. Is everybody following me so far? So 1 goes in the box, and then we write out the coefficients of our third degree polynomial, which are 1, minus 5, 3, and 1. Now you know. Bring down the 1. 1 times 1 is 1. Minus 5 plus 1 is negative 4. 1 times negative 4 is negative 4. 3 minus 4 is negative 1. 1 times negative 1 is negative 1. 1 minus 1 is 0. Box the last one. So remainder is 0. So x minus 1 is a factor. And so our quadratic is x squared minus 4x minus 1. We set that equal to 0 and solve for x. What kind of numbers are we gonna get? Are they gonna say what? They're complex. Yeah. Either complex or irrational, right? So let's set x squared minus 4x minus 1 equal to 0. Okay. A is equal to 1, B is equal to minus 4, C is equal to negative 1. Okay. You know what? I think I'll save this last little bit as a homework assignment for tomorrow. Okay? You figure out the last two zeros and the complete factorization of f of x. Okay? And we'll compare answers at the beginning of class tomorrow. Okay? So give you a little more time to take your quiz though.